So once we have done the bookkeeping of computing those matrices, this M matrices particularly, now we could state the result that let A and B be n minus 1 times continuously differentiable, then the n dimensional pair A comma B for the time varying case is controllable at T naught if there exists a finite time T1 greater than T naught such that the rank of the matrices formed by all these M matrices is equal to n, which is the dimension of the state. Okay, so here you would notice one thing, that so far we have discussed the results which were necessary and sufficient both, that we have studied if and only if, right? But here you would notice that we have only if, we don't have the only if, right? Meaning to say that this above theorem is only sufficient but not necessary. Okay, necessary in the sense that the system is controllable if this rank condition is satisfied, right? But if this or the rank of this matrix is equal to this, if the system is controllable, we cannot ensure that, the second statement. Okay, the other implication. So here there are a couple of things to be noted. So for if we are able to compute the state transition matrix, then we could have computed the controllability Gramian. Now the non-singularity of the controllability Gramian is a stronger result because it was necessary and sufficient both to prove the controllability. But now if it is not possible to, or if it is difficult to compute the state transition matrix, we have another result by which we can escape the computation of the state transition matrix. But this is a weaker result because it is not both necessary and sufficient, and in addition we require the n minus 1 times continuously differentiability of the matrices A and B, which was not required in the previous stronger result. Okay, so recall these two matrices, the M, basically the M matrix at 0 and at M is equal to 1 to n minus 1. So now we'll see the quick proof of this. So we show that if the rank condition holds, that the rank of that matrix, then WC T naught comma T1 is non-singular, right? Because we already knew that the controllability of the pair A and B is basically equivalent to saying that the controllability Gramian is non-singular. Okay, so now instead of showing that if the rank condition holds, then the system is controllable, it is equivalent to saying that if the rank condition holds, then the WC matrix is non-singular. Okay, so suppose not, meaning to say that WC T naught comma T1 is a singular or positive semi-definite for some T2 greater than or equal to T1, right? Then again there exists a non-zero constant vector V such that I could express this quadratic form equal to 0 because of the singularity of this weight matrix. Now we had seen in the earlier proof that the simplified form of this quadratic form, I can write this one, which implies that this is only possible if the vector inside the norm is itself equal to 0 or its transpose is equal to 0, right? For all tau in T naught comma T2, right? Now its differentiation with respect to tau yields as derived previously, in the sense that if I take the m times derivative of this part, basically I would come to this one. This is what we had done while having some bookkeeping of the defining the matrices, M matrices, and also their m times derivative for all m is equal to 0 to this one. Okay. Now if I arrange all these values starting from m0 to m minus 1, I could arrange this one also, because this is 0 for all m, meaning to say It would be 0 for m is equal to 0, m is equal to 1 up to m is equal to n minus 1. So I can arrange all these equations into a matrix equation which would become like this. Okay, which is nothing but equal to 0. Now note one point here. Initially we had assumed that WC is non-singular, oh sorry, singular, which ensures the existence of a non-zero constant vector, meaning to say V is non-zero. Phi being the state transition matrix is non-zero. So this would become equal to 0 only when this matrix is equal to 0, right? This matrix is equal to 0, which contradicts the rank condition. Because we wanted to prove this, but we proved the negation of that implication, that if the matrix WC is singular, then the system is not controllable, or the rank condition would not satisfy, sorry. Because the matrix itself is 0. So the rank of that matrix could not be equal to n, right? So this was the weaker results. Let's see one quick example so that it is pretty much clear of computing the state transition matrices and the additionally defined matrices. So for example, we are given this A and B matrix where we have specified m naught is equal to basically the B matrix, and looking at the dimension of this matrix, which is 3, we need to compute two matrices, m1 and m2, by using that formula we have introduced. So A of t is already given, m naught we had taken from the B matrix, and then the derivative of this m naught, okay, which would again be 0 matrix, because B is not time varying. Okay, so I computed this matrix m1 and m2, which are time varying matrices. Now if I arrange them as a matrix, I arrange them in the columns and then compute the determinant. Determinant come t square plus 1, which is non-zero for all t, meaning to say that this matrix is a positive definite matrix. If it is a positive definite matrix, then the rank condition would always be satisfied. Okay, you should not forget that in the week of the stability lecture, we have shown that you cannot compute the, so first of all, note that to show that the matrix is a positive definite matrix, in the stability week, we have computed the eigenvalues. We had shown that if the eigenvalues of the matrix are positive, then the matrix is a positive definite matrix. Now, we had also shown at that time that you can not use this computation of the eigenvalues onto the time varying matrices. Okay, now here M is a time varying matrix. So in order to show that this matrix is positive definite, you cannot use the eigenvalue test. Okay, because it won't satisfy. Right, so that's why we have computed the determinant and have shown that this determinant is non-zero and positive for all t. Okay, so this is a pretty much faster result. Now, since this is a sufficient condition, you should not forget that if the determinant happens to be 0, it does not mean that the system is not controllable. The system may still be controllable. This is because of that it is only a sufficient condition, not the necessary condition. So let's see the matrix test for the LTI system. Again, we have used a slash operator to denote the AB matrices for the continuous time case and for the discrete time case. So for the continuous time LTI system, we have already seen that both the subspaces are equivalent, and we do not need to talk about separately about the reachability and the controllability. But also we should not forget at the same time that in discrete time, this equivalence holds only when the matrix A is non-singular. Okay, in one of the examples in the week 1 we had seen that this A matrix is basically could be a singular matrix. Okay, so earlier we have seen this, the equivalence of all these three subspaces given by the controllability matrix, the reachable subspace and the controllable subspace. So since this controllability matrix has n rows, hmm, the image of that controllability matrix is a subspace of an n-dimensional space, right? So its dimension can be at most n. It cannot be greater than n, since because it is a subspace of an n-dimensional space. Okay. So for controllability, if you remember that this equivalence we had proved equal to the n-dimensional space, and therefore the dimension of image of the controllability matrix must be exactly equal to n, right? Based on this, we have the next result, that the LTI system, AB pair of the LTI, is controllable if and only if the rank condition of the controllability matrix is satisfied for the n-dimensional pair. Okay. So in the discrete time when A is singular, we simply have this inclusion but not the equivalence. So for the proof, we would see that the rank of C is equal to n implies that the reachable and controllable subspaces are equivalent to the n-dimensional space for the discrete time case. Now if it happens that the rank of the controllability matrix is less than n, it means that this subspace is equal to this subspace, which is a subset of this subspace of the controllable subspace, and this rank of C, matrix C, is less than n. One of the possible causes is that the matrix A is a singular matrix. Okay, so this was all about the matrix test, where we have a separate test for the time varying systems and a separate matrix test for the time invariant system. For the time varying system, we had two tests. One is the non-singularity of the controllability Gramian, which was a stronger result. A weaker result we had in terms of the computation of the additional matrices, M matrices. And for the LTI, we have the rank condition on the controllability matrix, which should be equal to n. Now the next test is the eigenvector test. So before stating the main results of the eigenvector test, we will introduce a couple of important definitions and results which would help us later to state the result of the controllability matrix in terms of the eigenvectors. So first definition is the A invariant spaces. So given an n cross n matrix a linear subspace V of the n-dimensional space is said to be A invariant whenever for every vector V belonging to this space V, we have this vector A into V should also be belonging to V. Okay, so you can see this in terms of the transformation also, that if we are given with any vector V belonging to this subspace V, this I can define by another vector W, and W, we have the transformation W is equal to A into V by this transformation matrix A. Okay, if that vector is formed by a transformation matrix given by A, and that vector W also belongs to that subspace, meaning to say that subspace is A invariant, that under the transformation of the A matrix A, the property of that subspace does not change, or the characteristics of that subspace do not change. Okay, so there are a couple of important properties of this A invariant subspace which we would going to use to state the eigenvector test for determining the controllability. So given a matrix n cross n of dimension n cross n, a linear subspace V, the following statements are true. So I wrote it in terms of the lemma, because we would going to see a proof of it as well. So the property one says that if one constructs an n cross k matrix V, okay, whose columns form a basis for that subspace V, mathcal V, then there exists a k cross k matrix big gamma such that AV equal V into gamma. Okay, so try to first visualize this lemma. What it says that if one constructs, I will repeat once again, that if one constructs an n cross k matrix V whose columns forms a basis for V. Okay, so let's say I define a V which is of dimension n cross k. Okay, now one way of writing this matrix is that I have k number of elements or k number of vectors, and each vector is an n dimensional vector. Okay, I can write this, which means that V1 is an n dimensional vector up to Vk, meaning to say this complete matrix would be an n cross k matrix. Now this subspace V, which is a subspace or which is a subset of an n dimensional space, this can easily forms a basis, meaning to say that if I have this A matrix, which is an n cross n matrix, okay, now I can write this n cross n matrix as A1, A2 up to An, where all AIs, I starting from 1 to n, is a row vector of n dimension. Okay, so every element here is a row vector of dimension n, which would give me the overall matrix of n cross n. Okay, so this elements of the matrix V forms a basis for V, which is an n dimensional space, right, which I can write with the existence of another k cross k matrix gamma is equal to this. So this A into V, you can imagine this into this. So A into V would be n cross k overall dimension, and for this V into big gamma would also be n cross k, because V is n cross k. Okay, so this, in fact, I just gave you the logical idea behind the proof. So we can see a formal proof. So since the ith column Vi of the matrix V belongs to V and V is invariant, right? If V is invariant, I would have ABI should also belongs to V, coming from the definition that if any element belongs to V, then the space being an A invariant would also satisfy this one. Okay, so this means that I can write AVI, the multiplication of the matrix A into the ith column of the matrix V, as linear combination of columns of V. And linear combination meaning to say that there exists a column vector gamma I such that AVI could be written equal to V into gamma I. Okay, for all I belonging to the set 1 to k. Okay, now if I just put all these equations into the form of a matrix starting from 1 to k, I would have AB1 up to AVk equal to, on the right hand side, starting from V gamma 1 up to V gamma k. So I could take a matrix out of common here, which is equivalent to saying that AV is equal to V into big gamma. Okay, where all gammas are used as columns for big gamma. Okay, so this is the first property. The second property says that subspace, which is an A invariant subspace, contains at least one eigenvector of A. Okay, so let's see the proof of it. So suppose let V bar is an eigenvector of the matrix big gamma corresponding to the eigenvalue lambda. Okay, So I can write this, I can write one equation based on the first statement, that big gamma into V bar is equal to lambda V bar. In fact, this equation you've been using to compute the eigenvalues, which you can write gamma minus lambda I V bar equal to 0, which means to say that for this matrix big gamma, there is an eigenvector V bar associated to the eigenvalue lambda such that this equation is satisfied. Okay, so starting from here, I pre-multiply this first equation by V. So I would have V big gamma V bar is equal to V lambda V bar. Right? Since lambda is a scalar, I can commute this with the matrix V. So I can write this lambda V V bar. Okay. Now in the first property, we saw that this part V into big gamma is nothing but equal to A into V, and this V bar. Okay, so this V bar comes from here and this comes from the upper part. Now let's define this V bar by another vector V. Similarly here, so I could write this equation as AV equal lambda V, which I can write as A minus lambda I V equals 0. So starting from this one, that V bar is an eigenvector of the big matrix gamma corresponding to the eigenvalue A. Now corresponding to the eigenvalue lambda, we found another vector V for the matrix A. Okay, meaning to say that V, the subspace V, contains at least one eigenvector of A. It might contain more than one eigenvector also. Okay, so this is the proof of the part 2 and both these properties. So this is the sketch of the definition and the properties. That first of all we have defined the A invariant subspaces, and then we have defined the property 1 of the definition, and the property 2 was defined based on the results we had obtained in the property 1. Now we would going to use this definition and these properties to give the eigenvector test. Okay.